These two sections are pretty short. So 3.13 is dealing with when we can neglect forces. And it really comes down to recognizing that when we're writing out forces, we typically only have enough information to write down a couple of significant figures. So let's say we've got F1, which has a magnitude of, 1.4 times 10 to the 8 newtons. Let's say it's some large gravitational force. And we've only got enough information to calculate this to two significant figures. And there's another force that we're dealing with, and it has a magnitude of, let's say, 2.3 times 10 to the 6 newtons. Now the thing to recognize here is that this 2 times 10 to the 6 actually doesn't appear until this significant figure right here that's missing. So this force is not actually going to change this force right here significantly. So if we go ahead and calculate F net, adding these two together, since we're only keeping two sig figs, this force becomes irrelevant. So one way to figure out whether or not a force is negligible or not is figure out how many significant figures you need to keep, and if one of these forces appears, or let me rephrase it, doesn't appear in one of the significant figure places of the largest force, then you know you can ignore it. If, on the other hand, we had three significant figures here, let's say that this was 1.43. This 2 times 10 to the 6 would occur there. It would affect that, and so calculating the net force, we would need to take this one into account. So it's really a matter of asking, when you calculate the net force, if one force dominates, will the other smaller forces actually show up? What you'll need to do if they don't is at least make an argument. You can either go ahead and calculate them and show, oh yes, this is so small it doesn't make a difference, or you can go ahead and make an argument as to this is, say, 1,000 times smaller than the other one or something. So let's say we're dealing with two gravitational forces. One where the mass of one guy is, say, 10 to the 24 kilograms. And in the second case, the mass is 10 to the, we'll say, 20 kilograms. And the distances in this case that we're dealing with are 10 to the 8 meters. And the distances that we're dealing with in this case are, say, 10 to the 10 meters. What we can do is we can make an argument that, well, this mass is 10 to the 4 times smaller. This distance is 100 times larger. Since the force of gravity depends on mass over radius squared, this force is going to be 10 to the 4 over 10 to the 2 squared smaller. So, and actually this should be negative, and so this is going to be roughly 10 to the 8 times smaller than that force. Clearly something that we can ignore. All right. The last thing is the very last section. I've mentioned this before, but when we're dealing with spherical masses, we treat them as if all that mass was concentrated right at the center point. What we say is that we model an object as a point particle, by which we mean it has essentially no size. And this just simplifies things because then we don't have to consider the fact that this thing is as a radius at all. We just treat it as being a point. And as long as these objects are far enough apart that they wouldn't bump in to each other, then that's really not an issue.